This is my video key, but it's also a chance for me to check the exam. So I might be finding errors, but this is my video key for fall 2025 for my online class for exam 2. So I'll start with the first one, substituent group 2-methylpropyl has the alternative name. Okay, so when I think of this, I think of okay, we have a parent chain, and off of the parent chain, I have 1, 2, 3 carbons, and then on carbon 2 there's a methyl. So this does look like the isobutyl group to me. And the way I kind of process these is if you have 3 carbons, you can either be propyl, so we have our parent chain 1, 2, 3, or isopropyl. If we so those are 3 carbons. If you have 4 carbons, it can, either be 1, 2, 3, 4, just a butyl, or it could be isobutyl, where it looks like 1, 2, 3. It looks like sort of, I numbered that wrong, I should say. It looks like a Y, but with an extra, like an isopropyl with an extra carbon there. Or it could be sec-butyl if it attaches at the second position, 1, 2, 3, 4. See how it attaches at the second position right there? And then we also have tert-butyl, which looks like this. So those are all of our 4-membered carbons, and then our 5-membered substituents, we have neopentyl, which looks like tert-butyl but with an extra carbon. So I kind of think these are the 3, these are the 4, and these are the 5, just to help you moving forward and for your final exam, of course. Okay, next question. What is the relationship between the following 2 molecules? Now, you can do this a few different ways. You can manipulate the molecule if it helps you, or you can envision yourself moving around the molecule. So for me, it's easiest to think about myself moving around the molecule. So for the one on the left, I'm envisioning myself floating above this molecule because the hydrogen is pointed, well, I guess maybe it would start better by saying the first thing that you could do to tell what's the relationship between 2 molecules is make sure it has the same number of carbons, hydrogens, everything else. So when I'm looking at these, I see 1, 2, 3, 4 carbons over here, and 1, 2, 3, 4 carbons over here. So 4 carbons in each one. Each has 1 chlorine and 1 hydrogen. So, okay, so these are definitely isomers of some kind. So they're definitely isomers. So we can remove not isomers, totally different molecules. And then we'll be left with constitutional isomers, diastereomers, or enantiomers. Nicely, I told you there wouldn't be diastereomers on this test. They'll come up on the next one. So instead, we can focus on constitutional isomers or enantiomers. Well, constitutional isomers would have different IUPAC names. So you could say 1, 2, 3, 4, 1, 2, 3, 4. So both of these are butane. And both of these have a chloro at the 2 position. So both of these are 2-chlorobutane. So these are likely enantiomers. Or they could be not isomers, the same molecule, but they're definitely not constitutional isomers because they have different, they have the same IUPAC name. So now the options are either these are the identical molecules or they're enantiomers. So if we're comparing these 2 things, that's when I start to visualize molecules to see if they're the same. So you kind of have 2 options. Option number 1, once you've confirmed, so I guess if I go through this, like step 1, confirm isomers. And then step 2, you can determine if they're constitutional or not. And then step 3, we're going to determine if they're enantiomers or another type of stereoisomers or not. We know we don't have diastereomers because that's not going to be on this test, but also there's 2 chiral centers at least for diastereomers. So the way that you can do that is you can either visualize the molecule or you can assign R and S configuration, whichever one works for you. And with visualizing the molecule, you can either rotate the molecule or you can imagine yourself moving the molecule. So for me, it's easier for me to visualize that I'm floating above this molecule, because then the hydrogen would be pointed away from me, which is what it's supposed to be doing for the lowest priority is supposed to be pointed away from you for absolute configuration. And so if I'm going to visualize this molecule, I'm imagining that I'm floating above it. So if I was floating above it, I would have a CH3 group up and to the left, a chlorine down and to the left, and then on the right side, we have an ethyl group. So the chlorine is highest priority, then ethyl 2 and methyl 3. So this would be an S configuration of this molecule. And then over here, our chlorine's pointed away from us. So if I try to visualize myself where the hydrogen would be pointed away, I'm standing on this side, looking this direction. So the chlorine would be back into my right, the ethyl would be or out into the right, ethyl would be out into the left, and the methyl would be straight down. So if we do 1, 2, 3 here, this is also S. So I think these are two of the same molecule. So that's one way of determining it. Another way that you can do it is, so I'm going to erase all that, and instead I'll say if the hydrogen is pointing straight towards you, the way it is here, you can assign your R and S configuration as if the hydrogen's not there, 1, 2, 3. If you do that, it's R. But because it's pointing towards me and I need it to be away from me, I know that this gives me exactly the opposite of what I want. So this would give you S configuration. So the tricky thing on that is you just have to remember to switch it back. You know, it's like assign R S configuration, but double check to make sure your hydrogen is pointed towards you or away from you at the end. That same trick doesn't work if it's in the plane of the page. So I wouldn't do that on the molecule here on the left. But a second trick you can do is switch two groups. So if I switch these two groups, the chlorine would be going towards me and the hydrogen would be going away from me. So now I'll assign my priorities, 1, 2, 3. So this would give me R configuration, but I switched the two groups, so I have to switch it back. If you switch two groups, you get the opposite enantiomer, and so these are both S. So looking over from several different ways of checking, I can see that these are not isomers. Another thing that you can do if you're good at visualizing molecules is if you can imagine, this is something that Joey, our PLTL leader, talks about a lot, is holding one molecule and rotating the other three all in the same direction, or not one molecule, one atom. So like, for example, he would hold this CH3 steady and then rotate to get your hydrogen to go backwards. Or I guess we'd be rotating to try to get them in the same as the one on the right. So let me think about how we could do that. None of them are the same. So you'd have to rotate a few times. So I don't know if I would use that on this one, but if you wanted to, you could start by holding this steady. Yeah, no, this is hard for me to do. So that's why I don't do it this way. So I won't use this as your answer. Okay. So far, both of the answer choices have been correct. So I'm using this to make sure the key is right as well. Okay, which is the IUPAC name for the following compound? So I'm going to try to find a parent chain here. This gives me 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, 7. Okay, so I just found 7. And a trick with multiple choice questions, as you can see, do they have any bigger than that? So I definitely found heptane, which is bigger than hexane, so I can eliminate all of these, and now it's just down to these two. So we're going to for sure go with this as our parent chain. Now we have to decide how to number it. So you can number it 1, 2, 3, 4, 5, 6, 7. Or the opposite way, and I like to do different colors, 3, 4, 5, 6, 7. I'm going to find my substituents. Here's 1 and here's 1. So we have 4, oh sorry, I'll do it in the colors. So if we go with the maroon one, we have 3 methyl and 4 isopropyl. If we go with a navy colored one, it's 4 isopropyl and 3 methyl. Nope, 5 methyl. Sorry, I was looking at the wrong one. Even with color coding, I do that. So this is not the best option. We're going to go with maroon. So we can ignore all of these. Those aren't the numbers we're looking for. Now I'm going to combine this all together, and I comes before M, so I would name this 4-isopropyl. Actually, I'll do this in maroon. 4-isopropyl, because I comes before M. 3-methyl heptane. So that's how I would name it. I'm going to come down here and look, and it turns out that they used the IUPAC name, the standard name, not the common name. But I can still look at the substituent numbers and make sure they're right. So on this one, we have 5 and 4, which we decided was wrong based on being able to number it the other way. So 3 and 4 for my 2 is correct. But just to double check, I'm going to make sure that this is methyl ethyl. So if we have 1, 2 for our substituent, we have 1 methyl on an ethyl chain. So 1 methyl ethyl. And if I was naming it that way, then this methyl ethyl would come second. So I am confident that this answer choice 3, the last answer choice, is correct. Which of the structures below would be considered the Gauss position? Okay, so for a Newman projection, if we have our groups opposite like this, and I'll say these two that I circled are biggest, this would be anti, and it's staggered. Anytime the groups aren't laying on top of each other, it's staggered. But if the two biggest groups are opposite each other, then it's anti. Now, if you have two big groups next to each other like this, we consider that gauche, which is the French word for awkward, but also for left, I think, if I remember correctly. So I'm looking for two big groups next to one another. So let's see. Oh, I see that right here. And I see that right here and right here. Okay, so I must not have thought that through whenever I was making this. So I will probably adjust this question and ask instead which would be considered the eclipsed position. So I'll change this. This is my first error. This question will be slightly different when you see it on your test. Either I'll change the answer choices or I'll change what it's requesting. I'm not sure. I need to look at that. Okay, and then the next one, how many chiral centers are in the molecule below? So I immediately think of the rules are that it's sp3 hybridized, tetrahedral, and 4 different things are attached. So I'm going to eliminate anything that's sp2 hybridized, so right here, and we're only looking at carbons for this class, so you don't have to worry about the heteroatoms. But all the rest of them are sp3 hybridized, so now I'm going to eliminate anything with more than 1 hydrogen. So there's 3 hydrogens here, 2 hydrogens here, 2 hydrogens here. We're not looking at these heteroatoms, so those don't matter. So I only see 1 chiral center, and that's the right answer. Okay, next question. What is the name for the following molecule? All right, let's see. 1, 2, 3, 4, 5, 6, 7. So 7 means that this is hept, so I can get rid of, this answer choice is wrong. I can get rid of the hex right here and the hex right here, and I know it's going to be one of these 2 heptenes. And actually without, oh no, I'm sorry. I made a mistake. There's an alcohol here, and I wasn't even thinking of that. With an alcohol, the parent chain needs to be contained within that. So we have to use the one with alcohol, which is shorter. So I'm actually going to get rid of these heptenes because there's not a way to have the shorter chain. So it's hexene. I'm glad I caught that. So now I'm going to look at my substituents and number this molecule. So we have 1 all, and it has to be the alcohol is going to get the lowest number possible because it's highest priority, and then 2 isopropyl, and then 4 ene for our double bond. So now if I'm going to combine it all, we have hexane as our parent chain, 2 isopropyl hexane, but with parent chains, if we have alcohols or alkenes, it's a suffix instead of a prefix. So we're going to have 4-en, and I'm not going to write E because to write alcohol, you drop the E at the end, and then 1-all. So that looks like answer choice 2 is correct. Answer choice 3 is not right because it doesn't have the 2 and the 6 would be right in front of these numbers, and you need the alcohol to be the lowest number possible. And then also I forgot to say that the double bond is trans. So that looks like the right answer to me. Okay, next question. Would the following reaction happen as written? So is it going to favor the right side? So when I'm looking at questions like this, I'm trying to pay attention to the pKa. And when I look at this, it looks like my water went from having a hydrogen to not having one, having 2 to only having 1. So this must be my base, and that must mean this is my conjugate. Oh, wait, no, sorry. Dude, I don't know what's happening to my brain right now. This is my acid, and this would be my conjugate base. So this is the thing that loses the proton, gives up a proton and accept electron. So that's our acid. So this is my base, and this is my conjugate acid. So I always start by labeling, finding the thing that's the acid and the base, conjugate acid, conjugate base. And then I know that I can compare. I know that reactions always favor the less reactive sides, right? So the more stable is going to be the product. So we can quickly do that by comparing pKa. So we have our acid here and our conjugate acid here. Our acid of water, the pKa is 15.7, and the acid of an amine, the pKa is around 38. I don't have my pKa table. Whenever you print the key, for some reason it doesn't include the instructions, so I don't have the pKa table as part of this exam, although you will have it, or you do have it. So when I'm comparing these two, just make sure that you're looking for like the nitrogen that's neutral. You know, sometimes I'll see students, they'll accidentally put nitrogen as being 9 or 10 because it's positively charged. So the pKa of that is 38. So I would say that yes, this reaction is going to happen as favored because this would be the favored side. So it would favor the right side. So I can immediately eliminate all these that say no. And now it's down to just 2 with yes options. So the 2 yeses, try to explain it. Yes, water would give up a proton because the resulting conjugate base would be stabilized by resonance. I don't see any resonance, so that one doesn't look right to me. Yes, water would give up a proton because the resulting conjugate acid would be a weaker acid. Okay, that makes sense to me, so I'm going to go with that one. I'm going to probably change this question to include it to say, explain how you know, because there's 2 parts to that one. Okay. Next question. The most stable conformation of this, viewed through the C2-C3 bond, is which? So first I'm going to draw this molecule out. Pentane is 5. 1, 2, 3 bromo, and 2 methyl. Through C2 to C3. So the front carbon is going to have a methyl, and a hydrogen. And the back carbon is going to have a bromine, a CH3 group, and a hydrogen. Let's see. More stable has the bigger groups further apart. So I'm looking for that, but the first thing I'm going to look at is like which one of these is actually even an appropriate structure. So we need hydrogen and 2 CH3s on the front. It actually doesn't matter if they're on the left or the right or what their configuration is because we weren't given R or S. So they did not tell us the chirality, just which molecules were where. But they did tell us to look through C2 to C3. So C2 needs to have 2 CH3s and a hydrogen. So this has that. This one, the front carbon has the bromine on it, so that's wrong. This one has the bromine on it, so that's wrong. This one has 2 CH3, so that's good. This one has the bromine on it, so that's wrong. So I actually don't have to do anything else. But I am going to double check and make sure the back one has the right thing. So just to make sure I didn't miss anything. Oh wait, no, there's 2 possibilities, 1 and 5. So I'm going to double check and make sure the back one's correct too. So the back one here has hydrogen, and ethyl, CH2, CH3, and a bromine. So the back one here has hydrogen, a bromine, and CH2, CH3. So that one looks right. And then this back one has hydrogen, bromine, and just CH3. So that one's wrong. So answer choice E is our only option. We don't even have to consider which one is going to have the most groups close together. So that's how I'd approach that question. Which of the following is the correct structure for S2-pentanol? Okay, so first I'm just going to make sure these are all 2-pentanol. So this first one, this is cyclopentane, so cyclopentanol, so that one's not right. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Both of those have 5 carbons, and alcohol, I should have numbered from that side, but alcohol on the second position. So both of these look like 2-pentanol to me, but we don't know if they're R or S. And then this one, 1, 2, 3, 4, 5, has a methyl at position 4. So we can narrow it down to just these 2. I don't even have 4 as an answer choice, so there you go. And then I should probably add it. That way I remember. Okay. Then I'm going to do the RS configuration. I'm going to do the one on the left first because the hydrogen's already pointing away from me. So that makes my life easy. So alcohol, the oxygen, and then we have 2 carbons. The carbon on the left has 2 hydrogens and another carbon, so it gets priority. So 1, 2, 3. This is S configuration, so answer choice 2 is correct, and we need to make a lot of changes to this one because I didn't select the right answer, and I'm missing an answer choice. But all the rest of them, it looks like, okay, yeah. I've circled the answer. Oh, this one's wrong too, gosh. I'm gonna double check this one. I noted that I need to fix that one. Okay, just double checking myself here. All right, next question here. Identify the most stable conformation of trans, 1-ethyl, 3-methyl-cyclohexane. So when I'm thinking of trans and cis, I will usually draw cyclohexane, the chair, out and think about which one is axial versus equatorial because it alternates, axial, equatorial, axial, equatorial. So we have 1-ethyl, 3-methyl. When I'm looking at these, ethyl is the bigger group than methyl, so I'm going to try to put ethyl equatorial. So I'll start with my ethyl here, and I'll make this position 1, and then 2, 3. So we want them to be trans, so if there's a methyl here, it should be axial. So I want my ethyl to be equatorial and my methyl to be axial. That's what I'm looking for. I can go ahead and draw this out. Just to sort of help myself and for y'all to see what I mean. So we'll put our ethyl equatorial here. It's equatorial down to 3, so then we need an axial up for our methyl. So I'm looking for something like this. So first I can go through, and any that are pointing both up or both down. So this has 2 pointed up, so that both of those being pointed up is cis. This one has 2 pointing down, so both of those being pointed down is cis as well. So these 3 all have 1 up, 1 down, 1 down, 1. Oh, nope, both of these are down, so that's cis as well. 1 up, 1 down. So I narrowed it down just to 1 and 5 just from that. But the most stable conformation has the largest group equatorial, so that would be E, or 5. Okay. This is a conformation as well. 1 is a conformation, it's just not the most stable conformation. Okay, identify the absolute configuration of the chiral center in the molecule below. So here's our chiral center, which we know because we looked at this molecule already once and had to find the chiral center, but also because it's the only one with any 3D arrangement. So that's how we know. So now I'm going to draw in the hydrogen here. And I am going to just we know hydrogen is the lowest priority, then we can pretty much ignore it. We have a carbon, and an oxygen. So oxygen being at priority 1 is the highest, or being the heaviest is at priority 1. And then we have 2 carbons, and then we have to look at what those carbons are attached to. So a lot of times I'll make a list. So for the top one, it's attached to, top carbon is attached to 2 hydrogens and an oxygen, hydrogen, hydrogen, oxygen. And then the bottom carbon is attached to 2 hydrogens and an oxygen. Okay, so they're actually still all attached to the same thing, so that doesn't help us at all. So then we have to keep going down the chain. So then the top oxygen is attached to another carbon, whereas the bottom oxygen is attached to a hydrogen, not a carbon. So this group on the bottom is actually the lower priority, so we have 2 and then 3. So this is S configuration, so S configuration. All right. Next question, which of the molecules below shows 2 methyl substituents in axial position? So we're just looking for axial. These 2 look axial to me, so I think that's right, but I'm just going to double check. Axial and equatorial, axial and equatorial, axial and equatorial. So answer choice A is correct. Next question, catalytic hydrogenation of which of the following will, first of all, I just saw that this should say none. Of which of the following will yield 2-methylpentane? So 2-methylpentane, 1, 2, 3, 4, 5, looks like this. So I'll draw these molecules out. So this is 3-methylpentene. So if we submitted this to catalytic hydrogenation, it would look like this. The next is 4-methyl-2-pentene. So 1, 2, 3, 4, 5, 4-methyl-2-pentene. So if we put that through hydrogenation, it will look like that. Just plain pentene, if we put this through, it doesn't even say where the double bond is. It could be here or here. I'll just pick one. That would just be pentane. So none of the above is our other option. So this one looks like 3-methylpentane. So that one's not correct. This one is 1, 2, 3, 4, 5. So this is 2-methylpentane. So that looks correct to me. And then this last one is just plain pentane, so that's not correct. So, and none of the above is also obviously not correct if we have one that's correct. Now this is tricksy because when you initially name it, your alkene takes priority, so the methyl is at position 4. But after you go through the reaction, the alkene is gone. So you're going to give the highest priority to the lowest substituent possible. So you start numbering from the other side and it becomes 2-methylpentene. So it's good to always draw these out. Okay, next question. Where would you place the following Newman projection on the energy diagram? So these are my 2 biggest groups. So I would expect that these 2 biggest groups are going to be as them being as far away as possible to each other. Well, let me start over. So we have 2 potential energies. The higher the energy is, the less stable the molecule is. Higher energy is less stable. Staggered is going to be lower in energy because the groups aren't laying right on top of each other. Whereas eclipsed, when we have our groups sort of laying right on top of each other, that is higher in energy. It's less stable. So that's our top one. So all these are eclipsed positions. We know for sure. And then all these are going to be our staggered positions. So we can immediately eliminate 0 degrees, which seems to be an eclipsed, 120 degrees, which seems to be eclipsed, and we know that our only options are 60 or 180. Now, it looks like 180 is the most stable, and that would be the one where you have the biggest groups opposite each other, and I think that that's what we have here, so I would go with 180. What I would expect 60 to look like would be to have the bigger groups still staggered but close to each other. So if you had your methyl and your ethyl right next to each other and then your hydrogens all close to each other, these two groups are going to have lots of energy repelling one another. And so it's going to be harder to get in that conformation than when they're completely opposite one another. So that's why I'm going to go with 180 degrees. Okay, next question. What is the relationship between the following molecules? So first, on our isomer diagram, if they're isomers, they could be constitutional or they could be stereoisomers. So we have 1, 2, 3, 4, 5 carbons here, and 1, 2, 3, 4 carbons here, 4, 5, 6. So actually, the first thing I always do is check to make sure they're isomers at all, and these are not isomers because they have different numbers of carbons. So hopefully you could tell just from looking that they weren't going to be enantiomers because they don't look like mirror images, nor diastereomers because they don't look like they have the same IUPAC base name. So the only options is not isomer same molecule or not isomer different molecules, and these are different molecules. Or I guess it could have been constitutional isomers as well. But if we have 5 carbons, then this would be a constitutional isomer that has sort of the tert-butyl arrangement. So these are totally different molecules. Okay, if you were trying to determine absolute configuration, what priority would you assign each area? So I am going to look at my chiral center and look at everything attached to this. So hydrogen, easy, it's going to be 4. So purple would be 4. Nice. Then I'll look at all these other things. So all of these are carbons, so that doesn't actually help me. So I'll make my little list and I'll color code it because why not? So in blue, we have a carbon that's attached to another carbon and 2 hydrogens. In orange, we have a carbon that's attached to 3 hydrogens. So already between these two, I know blue is a higher priority. And then in green, we have a carbon that's attached to 2 carbons and a hydrogen. So when I'm looking at these, I actually don't need to go any step further. Between these two, the extra carbon will win out. So if you eliminate, we have matching hydrogens here, so there's only 1 point of difference. There's 1 carbon here. So if this is position 3, this would be position 2. And then when we're comparing these two, blue and green, compare blue and green, we can see that there's a hydrogen is the same, a carbon is the same, they have 1 point of difference, and green has the heavier in that point of difference, so this would be position 1. So when you're looking at what the molecule is directly attached to, if they're all the same, you go to the first point of difference, and all of these had a point of difference at the first carbon, so I would rank green at position 1, blue at position 2, and orange at position 3. Okay. Now for this, is this the last question? No, there's a few more. Okay, name the molecule shown in the given Newman projection. Be sure to include stereochemical notation where appropriate. So when I'm looking at this, I'm going to number the carbon chain first. That's easiest for me. This is our front carbon, back carbon, 4, 5. So this is 5-membered carbon, pentane. And it looks like the only substituent it has is on carbon 2. And so I'm imagining we're looking at it from this angle. So I'm actually going to change how I drew this a little bit. We're going from carbon 2 to carbon 3. So carbon 2, 3, 4, 5. 4, 5 sticks down. So we'll go from carbon 2 to carbon 3. I'm going to try to draw it exactly how I see it. So from carbon 3, we have carbon 4 and 5 coming directly down in the plane of the page. At carbon 2, we have a hydrogen coming up in the plane of the page, and then coming out and to the right, so pointed towards me, if I'm looking from this direction, is an alcohol. And into the plane of the page is a CH3. So let me just make sure I got all my substituents right. We have 1, 2, 3, 4, 5 carbons. Check, check, check. We have a hydrogen, an alcohol, and a methyl on carbon 2, so that looks right. And then on carbon 3, we have 2 hydrogens and an ethyl, so that looks right. So I'm confident at this point that the parent chain is pentane, and we have 2 OL, so the alcohol in position 2, pentane. So this would be pentan 2 all. And then I need to assign R or S configuration. Now, I mentioned this before, but for R and S configuration, your hydrogen needs to be pointed directly away from you. If it's pointed directly, or the lowest priority needs to be pointed directly away from you. If it's pointed directly towards you, you can just assign the R and S configuration and be sure to flip it. But in this case, it's not pointed towards us or away from us. It's in the plane of the page. So I'm going to rotate all 3 of these. To get my hydrogen in the plane of the page, my alcohol will be pointed up, my hydrogen will be pointed back, and my CH3 would be pointed towards you. Okay, so that looks right to me. Did I rotate all those? Yep. So now alcohol will be the highest priority, priority 4 right here we don't need to worry about, 3 and 2, 1, 2, 3. So this should be R. And you're supposed to put it in parentheses, but if you don't, as long as you have the R, pentan 2 all, then you would get this question correct. So you'd get 1 point for the parent chain, 1 point for including the alcohol as a suffix, 1 point for including the number of alcohol, and 1 point for proper R versus S configuration. Okay. Next question, rank the bolded hydrogens from most acidic to least acidic. So for me, a lot of times I use my pKa on this, but you can also think about just the, the atom, resonance, induction, etc. for that. So when I'm looking at So when I'm looking at the bolded hydrogens, it helps me to highlight those bolded hydrogens. When I'm looking at the bolded hydrogens, I notice that 1, 3, and 4 are all connected to carbons. So then I'm thinking about the hybridization to rank those. And between them, we know that the more S character, the closer the negative charge would be held in the conjugate base if a proton is lost. So we know that 1 would be the most acidic of these 3, would be the least acidic. This would be the lowest pKa of the carbons. Then this would be the next to least of the carbons. And then this would be the third to least of the carbons because it has the most S character. If you're thinking about carbon, nitrogen, oxygen, and fluorine, carbon is the least electronegative, but as we go along the chain, more electronegative equals more acidic. So the next one I'm looking at is nitrogen, but it's positively charged. So that gives me pause. But it should be more acidic than any of the carbons, except, or I guess I'll say nitrogen in general should be more acidic than a sp3 hybridized carbon. But because we're dealing with more higher hybridization or sp2sp carbons, that's not always for sure the case. And because we're dealing with carboxylic acid, which is an oxygen with resonance, that's also not always the case. So once I realize, okay, I'm not going to be able to reason through this, that's when I go to my pKa table. And I think it's the easiest way to do this kind of question. So this pKa would be around 50. This pKa would be somewhere from, 9 to 10. This pKa would be around 44. This would be around 25. And this would be somewhere from 4 to 5. So that is going to be easier for me. And I also have a lot of these memorized. So that helps it go faster. You do have the pKa table available to you though. So I know this carboxylic acid, which is the most electronegative atom and it has resonance, is the most acidic. So that checks out with reasoning and with pKa. And then normally I would think that this nitrogen would have a pKa of like 38, but because it's positively charged, there's an extra hydrogen, it has a much higher pKa, so it'll be next. But in general, nitrogen is more acidic than like a sp3 hybridized nitrogen is more acidic than a sp3 hybridized carbon. If they're both neutral, everything's the same. So that's something to think about. And then We know we have our pKa of 25 next, and then our pKa of 44, and last but not least, our pKa of 50. So that is how I would rank these. Okay, the very last question is ring strain on cyclical molecules is made up of two different types of strain. Name and define each type of strain. So there's two types of strain. One is angle strain, and the other is called torsional strain. So you'll get a point for each of those names. If you said torsion strain, that's fine too. So you'll get, I guess, actually half a point for each of these names. So plus half a point for each of these names, and then half a point for the definition. So angle strain is the amount it deviates from 109.5. Now, if you gave any logical explanation, if you're like, rings would be 109.5, but if they take in a specific shape, then they have to be smaller angles than that. As long as it makes sense, you'll get half a point for the definition as well. And then for torsional strain, that is, I think, a little bit harder to describe, but it's essentially if your substituents or hydrogens, however you want to say it, if it's, just basic, so you just have hydrogens, being eclipsed or being really close together, those are going to repel each other and together. It's hard to spell and talk at the same time. Those are going to repel each other, and it will strain them to be close together. And these two types of strain are actually, torsional strain is the biggest reason that cyclohexane bends out of the chair conformation. Okay, I hope that was helpful, and I'll be sure to make these adjustments before I publish the exam, and I hope you all have a happy, I don't know what day of the week it is when you're going to see this, so I hope that helps. Good luck studying.